Imagine Kagome Metals as a playground for electrons, where instead of moving freely like cars on a wide highway, they have to navigate a maze of intricate triangular pathways, similar to how a skateboarder weaves through a park full of ramps and obstacles. This unique arrangement leads to unexpected and exciting behaviors. For instance, these metals can exhibit something called flatbands, where electrons slow down dramatically, similar to how a skier might stop on a flat stretch after zooming down a slope. This slowdown can create opportunities for the electrons to interact in new ways, leading to exotic states of matter like superconductivity, where electricity flows with no resistance, or spin liquids, where the magnetic properties remain in constant flux, rather than freezing into a fixed pattern, like a liquid swirling endlessly. Another fascinating aspect of Kagome metals is their ability to support quantum phenomena like the quantum spin Hall effect, where electrons with different spins, like tiny magnets, move along the edges of the material without scattering or losing energy. Imagine a racetrack where only cars of a specific color are allowed to race around the edge, while the rest of the track remains empty. This is how Kagome metals manage the flow of electrons. These unusual behaviors make Kagome metals incredibly exciting for researchers, as they could be used in creating future quantum technologies, such as super-efficient circuits and advanced quantum computers. These unique structures, named after a Japanese basket weaving pattern, are two-dimensional arrangements of atoms. The name Kagome itself is derived from the traditional Japanese craft of basket weaving, where the intricate patterns resemble the atomic arrangement in these lattices. They consist of interlaced triangles, forming a mesmerizing honeycomb-like pattern with intriguing properties. This geometric arrangement is not just visually appealing, but also fundamental to the unique physical properties that Kagome lattices exhibit. The beauty of Kagome lattices lies not just in their aesthetics, but also in their unusual symmetry. This symmetry is a key factor in the way these lattices interact with electrons and other particles, leading to behaviors that are not seen in more conventional materials. This symmetry, distinct from that of ordinary lattices, plays a crucial role in dictating the behavior of electrons within these structures. In ordinary lattices, electrons move in predictable ways, but in Kagome lattices, their movement is influenced by the unique geometric constraints. Imagine electrons hopping from one atom to another, navigating this intricate network of triangles. This movement is not random but highly influenced by the lattice's geometry, leading to unique electronic properties. The Kagome lattice's unique geometry influences these electronic journeys, leading to exotic phenomena not observed in conventional materials. These phenomena include unusual magnetic properties, superconductivity, and the potential for new types of electronic devices. These unusual properties open the door to a new realm of possibilities in the world of quantum materials. Researchers are particularly excited about the potential applications in quantum computing and advanced materials science. The Kagome lattice's captivating geometry has intrigued scientists for decades. Early studies focused on understanding the basic properties of these lattices, but recent advancements in technology have allowed for more detailed and practical investigations. It serves as a playground for exploring the interplay between geometry, topology, and electron behavior. This interplay is not just a theoretical curiosity, but has real-world implications for the development of new technologies. This interplay gives rise to a plethora of fascinating phenomena, including unusual magnetic ordering, unconventional superconductivity, and the potential for new types of electronic devices that could revolutionize technology, and the emergence of exotic particles like whale fermions. These particles, which behave in ways that challenge our current understanding of physics, could lead to breakthroughs in quantum computing and other advanced technologies. Understanding these phenomena holds the key to unlocking new technologies and pushing the boundaries of our knowledge in condensed matter physics. The study of Kagome lattices is not just about understanding a specific material, but about exploring the fundamental principles that govern the behavior of matter at the quantum level. Kagome lattices, with their fascinating geometry, form the bedrock of a new class of materials known as Kagome metals. These lattices are named after a traditional Japanese basket weaving pattern, which features a repeating arrangement of triangles and hexagons. This intricate design is not just visually appealing, but also holds profound implications for the behavior of electrons within these materials. These materials, where the atoms arrange themselves in a Kagome pattern, are not your everyday metals. Unlike conventional metals, where atoms are typically arranged in simple repeating patterns, Kagome metals exhibit a more complex and intriguing structure. This unique arrangement leads to a host of unusual properties that scientists are only beginning to understand. They harbor a wealth of exotic electronic and magnetic properties, setting them apart from their conventional counterparts. For instance, the electronic properties of Kagome metals can give rise to phenomena such as topological insulators, where the material conducts electricity on its surface, but acts as an insulator in its bulk. This duality opens up new avenues for research and potential applications in electronic devices. In Kagome metals, the unusual arrangement of atoms creates a playground for electrons, leading to unique behaviors. Electrons in these materials can exhibit behaviors that are not seen in other types of metals. For example, they can move in ways that are influenced by the geometric frustration inherent in the Kagome lattice, leading to novel quantum states. One striking feature is the emergence of flatbands, where electrons become sluggish and highly correlated. In these flatbands, the energy levels of the electrons are nearly constant, which means that the electrons do not have much kinetic energy. This lack of kinetic energy forces the electrons to interact more strongly with each other, leading to highly correlated states. Imagine a highway where cars are forced to move at the same speed, creating a traffic jam. This analogy helps to visualize how electrons in flatbands behave. Just as cars in a traffic jam are forced to interact with each other more closely, electrons in flatbands experience strong interactions due to their limited movement. Similarly, in flat bands, electrons experience strong interactions, leading to exotic states of matter. These states can include phenomena such as superconductivity, where the material can conduct electricity without resistance, and various magnetic orders that are not seen in conventional materials. These interactions are further amplified by the presence of Dirac points, special points in the electronic structure, where electrons behave as if they have no mass. At these Dirac points, the electrons can move at very high speeds, similar to how photons move in a vacuum. This massless behavior adds another layer of complexity and potential for new discoveries in Kagome metals. The combination of flatbands, Dirac points, and the Kagome lattice's unique geometry creates a fertile ground for unconventional superconductivity, exotic magnetic ordering, and other intriguing quantum phenomena. These combined effects make Kagome metals a hot topic in condensed matter physics, as researchers strive to uncover the full range of their properties and potential applications. Kagome metals, therefore, represent a frontier in condensed matter physics, offering a glimpse into the bizarre world of strongly correlated electrons. The study of these materials is not just about understanding their fundamental properties, but also about exploring how these properties can be harnessed for practical applications. Their unique properties hold immense potential for technological applications, particularly in quantum computing and spintronics. In quantum computing, the ability to control and manipulate quantum states with high precision is crucial, and the exotic properties of Kagome metals could provide new ways to achieve this. Similarly, in spintronics, where the spin of electrons is used to store and process information, the magnetic properties of Kagome metals could lead to more efficient and powerful devices. Kagome metals' properties, governed by the intricate dance of electrons within the Kagome lattice, hold the key to unlocking their extraordinary behavior. The Kagome lattice, named after a traditional Japanese basket weaving pattern, creates a unique playground for electrons, leading to behaviors that are both fascinating and complex. Unlike conventional metals, where electrons zip around freely, Kagome metals present a unique challenge. In traditional metals, electrons move in a relatively straightforward manner, allowing for predictable electrical conductivity. However, in Kagome metals, the story is quite different. The Kagome lattice's geometry forces electrons to interact strongly with each other, leading to a phenomenon known as electronic correlation. This interaction is not just a minor detail, but a defining feature that gives rise to the unique properties of Kagome metals. Imagine a crowded room where people constantly bump into each other, influencing their movement. This analogy helps us visualize the complex interactions between electrons in a Kagome lattice. Each electron's path is affected by the presence of others, creating a dynamic and ever-changing environment. Similarly, in Kagome metals, electrons are in constant interaction, affecting their energy and momentum. These interactions lead to a rich tapestry of electronic behaviors that are still being unraveled by researchers. This electronic chatter leads to the emergence of exotic electronic states not found in ordinary materials. These states are not just theoretical constructs, but have been observed in laboratory settings, providing a glimpse into the potential applications of Kagome metals. One striking manifestation of these interactions is the appearance of flat bands in the electronic structure. Flat bands are a direct consequence of the unique geometry of the Kagome lattice and the strong electronic correlations present in these materials. Flat bands, as the name suggests, are regions in the electronic structure where the energy of electrons remains almost constant regardless of their momentum. This is a highly unusual feature that sets Kagome metals apart from other materials. This is akin to a flat road where cars can travel at various speeds without experiencing a change in gravitational potential energy. In the context of Kagome metals, this means that electrons can move through the material without significant changes in their energy, leading to unique electronic properties. These flat bands, a direct consequence of the Kagome lattice's geometry and electronic correlations, play a crucial role in the emergence of exotic phenomena like unconventional superconductivity and unusual magnetic ordering. These phenomena are not just academic curiosities, but have potential applications in next-generation technologies. Understanding the nuances of these electronic properties is paramount to unraveling the mysteries of Kagome metals. Researchers are continually exploring these materials, hoping to unlock new possibilities in electronics, quantum computing, and beyond. The journey into the world of Kagome metals is just beginning, and the potential discoveries are boundless.